Okay, so today we're going to talk about the Lorentz velocity transformations, and here's just a picture of it. I'm going to first, well, that's just it, but first I want to mention that I'll rewrite these down in kind of the terms we're used to in our book, that if an observer O, let's word it like this. If O observes a particle, that travels at velocity we'll just put it down here, I guess. V equals, well, we'll write its components out. V sub x, V sub y, V sub z. O prime measures, and I'm going to write these in the way we're familiar with. So V prime of x, the velocity from V prime's point of view, is Vx minus u all over 1 minus Vx u over c squared. V prime y equals Vy, the square root of 1 minus u squared over c squared, all divided by 1 minus Vxu all over c squared. And lastly, V prime z is equal to Vz times the square root of 1 minus u squared over c squared, all over 1 minus V sub x u over c squared. So right here, these are Lorentz velocity. That's a really bad Z. Transformations. Okay. Now notice what happens. Notice what happens when U is much smaller than C. Well, in that case, these all break down to our Gaussian transformations. So like V prime of x. Well, if this is U is much smaller than C, right? That's essentially going to be just Vx minus U over 1, so just Vx minus U. And that's the same thing for all of these, really. Because what will happen is this will be the square root of 1 over 1, so that's just Vy. And the same over here. And the same thing happens over here. This is basically going to be the square root of 1, right? Because this is so much smaller than this that it's essentially 0. And this is basically going to be 1 minus 0. So they all break down, which is good. That's what we've seen kind of repeatedly. That was a bit of our theme with the Lorentz transformations, is they should break down into, at low speeds, they should break down into what we see with our Gaussian transformations. So first off, let's prove. First off, let's prove V prime y. Now, if you remember, we said that T prime is equal to T minus Ux over C squared, all over the square root of 1 minus U squared over C squared. Now, differentiating, delta T prime equals delta T minus U over C squared delta X all over the square root of 1 minus U squared over C squared. So we just replaced our variables with these very, very small changes. Now remember, v prime of y is dy prime over dt prime. Well, this should only be under here. Let me lasso that guy in. There we go. Oops, brought us to the top. There we go. So this, well, in our denominator, we're going to have dt prime. So that's going to be dt minus u over c squared dx. And that's all going to be over the square root of 1 minus u squared over c squared. And then we have dy prime at the top. Okay, so a little messy, but if we flip it, that's the same thing as square root of 1 minus u squared over c squared times dy prime all over, well, what do we have? We have delta t minus u over c squared delta x. And we can factor delta t out from the bottom. So let's do that. Times dy over dt, 1 minus u squared over c squared dx dt, if we factor out the dt, right? Which is the same thing as the square root of 1 minus u squared over c squared times dy dt all over 1 minus u squared c squared dx dt. Okay? Well, what's dy dt? Dy dt is just vy. And what's dx dt? That's just vx. So what we can say is v prime y is equal to, this is just a vy, times the square root of 1 minus u squared over c squared, all over 1 minus u squared over c squared times delta x, but dx dt, but that's just vx. Did we get it? Let's see. Vy square root 1 minus u squared over c squared, 1 minus vx u. Did I square the u when I shouldn't have? I did, sorry. This shouldn't be squared. This shouldn't be squared. That should be squared. I think I was looking at this guy over here, but that one's not squared. This c is squared though. So yeah, there we go. There is our velocity transformations. So this is if you had some object or some reference frame moving, and how you can relate the velocities of a stationary observer to a reference frame that's moving with a particle moving in it. Okay, so u is how fast the reference frame is moving, and v is how fast that thing in a reference frame is moving. So just to give you an example of what you might mean or what you might see, you know, if you had like a train, say you had a train moving at speed u, and then here I am on the outside, you're on the inside, and let's say you roll a ball at speed v. How fast I measure it compared to how fast you measure it, well, we could use a Galilean transformation, but let's say u is getting closer to the speed of light c, this theoretical train. Then we have to use these transformations that'll relate how you see it compared to how I see it. So hopefully that makes sense, and I will do another video tomorrow.